Hello, welcome back. We're going to talk a little bit about linear speed and angular speed and how they're related, and look at some problems where we have to, apply formulas that we're going to come up with. Now, when you guys hear about speed, typically in conversations we're dealing with linear speed. Like if you're talking about how fast you drive. We tease, my husband and I tease my father-in-law's wife about how fast she drives because it seems like she can get halfway across the state in like an hour when it takes us 2.5 hours. But anyways, when you talk about driving and stuff, when you talk about your speed, like here in the United States, we typically talk about how many miles per hour we're driving. The line here is the per. And that comes from speed being found by dividing your distance by the amount of time it takes to cover that distance. So speed equals distance over time. The miles is your distance, and then the time is the hours. But that's linear, because like usually when you think about driving somewhere, you're going from point A to point B, and you're looking at how you might drive straight, you might turn, that kind of thing, but you're still looking at driving in a two-dimensional kind of manner. But that's a linear speed. So we're going to take that formula and we're going to play with it a little bit. In your book, you'll see, or in physics books, often you'll see instead of speed, instead of s, they'll say v, like for velocity. And then instead of the d for distance, we're going to end up replacing that with s, and then we'll still keep t for time. Because we are going to start looking at the same kind of formula in terms of what's happening on a circle. All right, let's say let's draw an angle here real quick. All right, just need to have that on hand. Let's see. I couldn't finish it. Let me undo that. Try again. Sometimes it's like my pen catches on my tablet here or something. Okay, let's say we have this angle here, and we want to talk about a point on the angle or a point on the circle moving around. Okay, so let's say we have this point right here, and and then we want to see what's happening as it moves on the circle. So then let's say it ends up here. Okay, as it's traveling along the circle, we are interested in two different speeds. First, the linear speed is the speed of as it changes its position as it moves on the circle here. That's the linear speed. So the distance that it's traveling is an arc length, s. So as the point goes from here, from 1, 0 to here, or whatever this is to here, the distance it travels is arc length s. And we're looking at, well, what is that distance in relation to the amount of time that has passed as it goes from maybe, point B, we call this point B, to point P. And that's where this comes from here. It's like velocity or speed equals the distance, in this case the arc length s, divided by time. And that's very linear. Okay, but then we can also measure what's happening as far as the angles are concerned, as far as looking at your thetas. As the point moves along, you have this ray that's following it, and then they're going to call the origin O. You have this ray OP that the point, you can go from the origin through the point P, and as the point moves, you can let that ray move with it, and as it's moving, we have a change in angle. And we can measure the angle changes as well. We can measure the theta changes. And that's something called angular speed. So not only can we look at the point's actual distance in relation to its time, but we can also look at what's happening to this ray that goes through the point, to the angle change with respect to time. Okay, and they go ahead and call angular speed omega. It looks like a W, like a little round W. But instead of distance, we're looking at angle changing, theta changing with respect to time. And that gives us angular speed. And this will be, the theta will be, we're talking about radians here as we do this. Okay, so that's an important formula. But there's some really cool manipulation we can do. Remember how S equals R theta? We learned that not too long ago. If you've been listening to podcasts all at once, you just learned it. Well, we can take V equals S over T, and we can replace the S with R theta, and then have something really cool happen. Separate R times theta over T, and it turns out that's really omega. So the linear speed is related to the angular speed. If you take the angular speed times your R times your radius, you can get your linear speed. Pretty cool, huh? So that's how those are related. All right, well let's do some problems where we use these formulas. Okay, I'm going to scroll down. Let me rewrite the formulas real quickly. Here we got angular speed, omega equals theta over t. Remember, theta is going to be in radians. And then we got linear speed. Velocity is change in arc length over change in time. But then we can rework that, and that's related to angular speed by doing the radius of your circle there times omega. All right, let's say we've got a point P. It's on a circle with radius 15 inches. And let's say it's let's say that ray OP is rotating with angular speed pi over 12 radians per second. All right, a couple things we can do. First of all, let's find the angle generated by P in 10 seconds. So we have circle, we have some point P on the circle, circle has a radius of 15 inches, and we've got center is O, origin. OP, this ray here, is rotating around the circle with an angular speed of pi over 12 radians per second. So it's moving in a counterclockwise direction, pi over 12 radians every second. Okay? And the radius of the circle is 15 inches. Well, angular speed is the angle over time. They tell us the angular speed, okay, so let me rewrite that. Angular speed is the theta over time. They tell us the angular speed is pi over 12 radians per second. And we're trying to figure out the angle theta generated by P in 10 seconds. So if we multiply both sides by 10 seconds, we'll be able to solve for theta. Pi over 12 radians per second times 10 seconds. seconds will reduce, leave you with 10 pi over 12 radians, or 5 pi over 6. Okay. So 5 pi over 6 radians. Now, I say find the distance traveled by p along the circle in 10 seconds. They gave us the angular speed, but now they're asking about distance. Like, as it's traveling, how far did it go? If you track its path along the circle and like lay that out flat and measure it, how far, how long are we talking about? But remember, we got a couple of things up here we can like try to look at and see what might be useful. We know time, we know angular speed, we know the radius, etc. So let's see here. Angular speed and the radius multiplied together give you the linear speed. What else we got? We also got S equals R theta still. That's still in our background. Let's see. They gave us find the distance traveled. So distance traveled, really you're trying to figure out what S is. You know the radius. And we just figured out the angle generated in 10 seconds. So we can use S equals R theta. We got plenty of information to do that. Let's see here. Because we just found out that as point P is traveling, we figure out the angle generated in 10 seconds would be 5 pi over 6 radians. And we can take the radius of 15 inches and multiply that. And since radians isn't really a unit of measure, when you multiply these two together, your answer is going to be in inches. So we'll have 75 pi over 6 inches. And that'll reduce. Let's see, 3 goes evenly in, so you get 25 pi over 2 inches. So there's an exact answer. If you want a decimal approximation, just do 25 times pi divided by 2 and see what you get. Okay, then let's see here. How about next we figure out, find the linear speed of p in inches per second. Alright, we got some linear speed info. We know linear speed, V equals S over T, or R times omega. Let's see, so what do we got so far? We know S for 10 we know S for 10 seconds. So there you go. We're trying to do it per second. Well, if it's moving 25 pi over 2 inches per 10 seconds, you got that in the previous problem there. And we can go ahead and simplify this to figure out how many inches per second it's going to be. So we got 25 pi over 2 times 1/10. So 25 pi over 20. Let's see, 5 will go in evenly, so we get 5 pi over 4, and that's in inches per second. And there's the exact answer there. Okay. Let's see. There's another situation. Let's do it. Another example problem dealing with pulleys. Let's check it out. Extend the page here and do another example problem with you. Got an example where a belt runs a pulley. So you've got a pulley with some kind of a belt pulling it. While I'm drawing this, it just reminded me, I was thinking about what I did last weekend. Last weekend, before I made this podcast, was Labor Day weekend. And we went down the Atlantic coast to some place called the Elliott Museum, like down in Fort Pierce. And they were just the last day of the Leonardo da Vinci exhibit. And if you ever get a chance to really read about Leonardo da Vinci, he did some amazing designs for machines that use all kinds of pulleys and stuff. And he wasn't the first to come up with some of the basic concepts of what his designs, his machines, but just the way he put things together. But pulley systems, you can use a series of wheels and ropes or chains or something to make it much easier to lift something. A good pulley system rigged can allow a single man to lift an entire truck out of the mud or something if it's well rigged. But anyways, okay, we got a pulley, so we got this wheel basically, and there's this like chain or rope attached to it. And this pulley system, we've got a belt. The pulley has a radius of 5 inches. And it's moving at 120 revolutions per minute. So in other words, as this chain moves, it's making this circle move, and it's doing 120 revolutions per minute. So the circle, like if you have a point right here, that point's coming all the way around back to where it started 120 times every minute. We have to find the angular speed, and we're going to find it in radians per second. We also have to find the angular speed for the pulley, the circle, the wheel. And then for the belt, we have to figure out its linear speed in centimeters per second. So angular speed, how quickly is the angle changing here? And then linear speed, how quickly is this belt, if there's a point on the belt somewhere, how quickly is it traveling along a distance on the belt? So that's the speeds we want to make. Alright, so in 1 minute, the pulley makes 120 revolutions. Each revolution is 2 pi radians. Remember, revolution, just point starts here, goes all the way around. That's traveling 2 pi radians, an arc length of 2 pi radians. Okay. So what's happening there then is 120 revolutions times 2 pi radians for each one. It's going to equal 240 pi radians per minute. Now there's 60 seconds in 1 minute. And we'll use that to help us figure out radians per second. So to take 240 pi radians per minute and multiply by 1 minute over 60 seconds. Minutes will cancel, and you end up with 4 pi radians radians per second. So that's your angular speed. So if you're following this point going around, every second that point travels, goes through an angle of 4 pi. So every second this point goes around once, goes around again, and comes back to where it started. So it goes around twice, 2 whole revolutions, every second. Okay, that's the angular speed. Then the linear speed, we're interested in seeing what's going on with that point on the circle, on the wheel. Well, the 4 pi radians per second, since that is angular speed, that's omega. So we can use our formula that of linear speed being the radius times omega, make that a little rounder to make it look more like omega. We know the radius of this pulley was 5 inches. Times that by the 4 pi radians per second. Multiply, you're going to get 20 pi inches per second. If you want to, you can multiply 20 times pi in your calculator and see what that comes out to. You get around about 63 inches per second. So if every second, not only is the angle, you know that it's going around 2 times every second. So what's happening, because the angular speed, 4 pi radians per second. So then what's happening with linear speed is that this point is traveling the circumference twice. Well, if you do the circumference is 2 pi r. 2 times pi times the 5, you get 10 pi inches. That's the circumference. And if it's going around the circumference twice every second, then it's doubling this. It's going 20 pi inches every second. 20 pi inches per second. So when you look at linear speed, you really are looking at what part of the circumference, how much of the circumference is it traveling per unit time, per second or whatever. But the formulas we are using, like the V equals R times omega, it makes it very efficient to figure it out. I mean, you could go through and do the circumference and then figure out, well, what fraction in that time period would it travel, and then multiply by that fraction. In this case, it's double twice, so you multiply by 2. But if it only goes like 1/3 of the way, then you multiply by 1/3 or something to see the linear speed. But that's the correlation between, there's a correlation there directly with linear speed and circumference. Okay, well, I hope you enjoyed some of these application type problems. We're learning about linear speed, angular speed, and doing some application problems with those. Make sure you're familiar with these formulas, because you will be using them for testing situations, and they will not be provided for you. So you want to make sure you've got these formulas in your head. Know how to use them, know what's in them, etc. Okay, well, have fun with that, and I look forward to seeing you again next time.